All right. Good morning, everyone. Welcome back. Thank you for joining BrainMap today. This BrainMap Seminar Series is co-sponsored by the P41 funded Center for Mesoscale Mapping, Houghton Martinos Center. It is my pleasure to introduce our today's speaker, Dr. Markus Axer. Dr. Axer is Deputy Director and Head of the Group Fiber Architecture at the Institute of Neuroscience and Medicine in Jülich, Germany. He's a physicist and oversees the development of 3D polarized light imaging technology to reveal the brain's structural connectivity and fiber architecture. This includes the design of polarimetric microscopes, the implementation of image processing algorithms, and big data analytics, utilizing high-performance computing. Markus' group is developing simulation tools to investigate the interaction of polarized light with brain tissue at geometrical optics and computational electrodynamics levels of the description. Today, he will talk about towards the nested connectome, bridging the scales with 3D polarized light imaging. Dr. Axer, the virtual stage is all yours.
Thank you very much for this nice introduction. Thank you very much for inviting me. And I'm really happy to give you some insights into the work we've done in the last 10, 15 years. And as you can see from my title here, of course, polarized light imaging is a fundamental technology in my research. So I will start with a brief introduction about this kind of microscopy, but I will also go deeper into other technologies we use to get into the kind of what we call the nested connectome. So addressing the connectivity of the brain at different levels with different modalities. So for those, let me see. Okay, so for those who are not familiar with this kind of technology, I will give a very brief introduction of the entire pipeline we have developed over the years. And everything starts, let's say, with famous Mr. Brodmann at the beginning of the last century. And you know him possibly as the man who developed the first, let's say, serious cytoarchitectonic map in the human brain. But he also wrote very early, 1903, the following sentence: I stumbled upon the idea of formalin-fixed tissue much later and realized with satisfaction that formalin fixation does not impair the birefringence of myelinated nerve fibers. Therefore, we can study nerve fibers hardened and conserved in formalin with polarization microscopy and observe possible pathological alterations. And this is what we are going for, what we try to realize. We want to utilize the optical property called birefringence to give contrast to myelinated fibers in the end. And the devices we use are called polarization microscopes. And this is, in the end, brought to nowadays research, state-of-the-art technologies, what we call the 3D polarized light imaging or 3D PLI. So as we can read it here, we need formalin-fixed brains. That means we have to go into the lab. We have to collect the brains from donor programs. Then after receiving the tissue, we put it in formalin for about 3 to 6 months. Afterwards, we do a surface photography and rebuild the surface mesh of the specific brain. We put it into glycerol, freeze it down to -80 degrees, and cut it in the end at -50 degrees in a cryostat microtome, as you can see on the top right here. We typically cut the brain into 50 micron sections, not millimeter thick sections, micrometer sections. We do need any staining because we want to use the birefringence of the fibers for giving contrast to them. In addition, we always acquire block phase images, which are simple photographs from the top of the block, right? And this block phase images we can use to reconstruct the brain tissue very quickly, and we can use this kind of reconstruction you can see on the bottom right side here for the 3D reconstruction at the very end after doing all the microscopic measurements. Of course, we also acquire MRI data sets post-mortem before we do the sectioning. So we do have two kinds of references available at the very end, MRI plus the block phase images you can see here. We have developed a couple of devices over the last 15 years, and two of those survived in the end and currently build the routine equipment. And the first one we call large area polarimeter, which is an or short LAP, which is an in-house design. So we produce it on our own, being able to measure the brain sections at 64 micron pixel size. So that means with this setup, we can image quite quickly. So that means quickly means 15 minutes per section, with isotropic voxel sizes of about 60 microns. The second device, which generates these fantastic high-resolution data sets you've seen on the cover slide, you see in my background, generates images of 1.3 micron pixel sizes. And these files are really huge. I will come back to this issue a little bit later. And this kind of microscope we call LMP1. It has been built by a very tiny company nearby Jülich. And we are currently also producing a new one. I will talk about this also a little bit later. So the general measurement principle is really simple. We need polarizing filters, and these are two linear polarizers, one quarter wave retarder, and these filters, they rotate around the fixed, the stationary sample, and we use green wavelength illumination source, and we observe then the intensities with a CCD camera. And when we do a rotation of all these filters, you see by eye, you can see these kinds of intensity changes. And these changes are effects coming from the birefringence. Here, this movie here is based on LAP measurements. That means you do not see pretty much resolution in the cortical areas, but don't worry, we will come back to this high resolution stuff a bit later. What you can see here are three different, so to say, monitors showing the change of intensity that we are measuring during the measurement process. And what you can observe is that you, independent of where you are in the deep white matter, you tend to see sinusoidal curves. But these curves do have different amplitudes and or phases. And these amplitudes and or phases, they give us information about the local 3D orientation of the birefringent structures, which are the fibers. So that means when we do analysis, we try to fit the intensity behavior in each acquired pixel. It looks like this here, right? So we have one exemplary pixel fitted, and we extract usually the mean value, the phase, and the retardation. And if we bring this into again into the section space, you can see here how the mean value looks like for an entire brain section. This is the phase image we call direction. Why I come to this in a minute. And this here, the amplitude looks like this, and this is what we call the retardation. And you see, you already have three different types of or modalities extracted just from the measurement signal at the same time. The transmittance map here shown here looks a little bit like at the first glance like a myelin stained image, but it is not exactly the same. So of course, up to now, when we do analysis just of a sinusoidal curve, it's just mathematics. And the question is, what are the neuroanatomical correlates to these different maps shown on the top? And we can make sense of it by using optical physics, matrix, calculus approaches, and with that we can have a very easy and simple model describing the behavior, the sinusoidal behavior of the intensity. And it shows immediately that it depends on the orientation of the nerve fibers projected into the sectioning plane on one hand side, but on the other hand side also on the out of sectioning plane angle of these fibers. And that's quite nice. We can try to extract them and build in the end orientation vectors in 3D telling us what's the local orientation of, saying it in physical words, of the optic axis in the specific voxel we are looking at is. So that means the direction here is the in-plane orientation, fiber orientation angle, and the retardation includes all the birefringence physics we have. It depends on the thickness of the material of the brain section. It depends on the local birefringence strength of the fibers and of the used wavelength. And it also depends on the out of sectioning plane orientation. Right. So the basic idea is to extract those values and then have a look into the distribution of the local fiber orientations. However, you can see it immediately that the out of plane angle depends also on other parameters which are not easily to be measured independently. So at a first glance, it's not that easy to get hands directly on the measurement of this alpha component. And we try to solve this problem in the next generation of microscopes. I will show you in a couple of minutes. But starting with this, we can produce those nice colorful images, right? So we extract the 3D vectors and give them distinct colors, as you know from diffusion MRI. So from the basic idea, it's the same, but you will, if you're used to look into diffusion MRI, FA data or something similar, you're used to use RGB color space, which is not our favorite color space, because we can measure at much more angular resolution. So we should also use a much more broadened kind of orientation descriptions. And this kind of map we call the fiber orientation map, or FOM, which is, let's say, one of the fundamental basic final results of the PLI approach. And you can also see, depending on what size, what resolution you are looking at, you can go for entire brain assessment at lower resolution, or you can also go into local regions, looking at very fine-grained microstructural cortical connections. And this is what we always try to do, making measurements at both resolutions, so that we always have these different scales available. As you can imagine, measuring an entire human brain, which is one of our final goals, is not possible without supercomputing aspects. So since we do not only have to, let's say, rebuild the 3D shape of the individual sections, but we also have to analyze every pixel, every voxel concerning this sinusoidal behavior. We need support of big machines. And fortunately, we do have big compute machines next to us at the same campus in Jülich. So one thing we have started to set up is a very dedicated kind of big data management and supercomputing workflow, so that we can generate images in the lab, save those images in HDF5 file format containers, including all metadata related to the individual section. Then we have an automatic quality control, because you can imagine if you have something like 7,000 sections measured within a very short time period and analyzed, we are not really able to look into individual pixels anymore. So we need some automated kind of quality control, just in case that the measurement did not work properly, so that we can simply repeat such a large scale scanning very close to the initial measurement. Then the data is transferred after the quality control is passed. It is sent to a quite complicated multi-tier HPC storage system, from where it can be accessed either remotely from our lab, or also, of course, remotely from the different supercomputer types we are using. So that's already kind of science on its own. I'm not going much deeper into this currently. So we already applied PLI technology to a couple of species. Here are just a few. So of course, mouse, rats brains are always the starting point for most of us. We have looked into monkeys, vervet monkey brains, human, of course, and also bird brains, like the pigeon here. We did zebrafish, and currently we have started to do some seal brain imaging. And it's really interesting to see how the individual, I like to call it the individual knitting patterns, change or are similar across different species. And of course, you can also see in this table here the different sizes of data to be expected. When you go to human brain imaging at a few micron scale, that always means you have to deal with petabyte of data in the end, a couple of petabyte even. So that's really just comparable to elementary particle physics data you have to analyze, and that's one of the challenges for all of us. What have we done so far in terms of individual section analysis? And yeah, so last year we were lucky to compare mammalian brains versus the pigeon brain here, and found similar structures, perpendicularly crossing structures. You can see here in the, so that's a sagittal section through the pigeon brain. And then we compared those, of course, to the much more well-known red brains, and found interesting similarities, which made this kind of imaging technique become a kind of also discovery tool, and that was very, very cool. We did applications on individual sections in the hippocampus together with Michael Zajny from Stanford University a couple of years ago, and all of these individual section delineations, they were triggered by Carl Zilles, right? So he was some of the founders of this technology in his institute 15 years ago. And he was always pushing towards also this kind of, let's say, more classical way of interpreting individual sections. Of course, we want to go to 3D reconstructions, 3D analysis, and you all know this problem of sectioning a brain. It's basically crazy to destroy a brain to get to know how the coherence and the connectivity throughout the entire brain is. But I know that you are all also know very well the optical coherence tomography, where you don't have to cut. On the other hand, one of the benefits from doing this classical sectioning approach is that you have the possibility to measure really large areas within a section. However, still we have to deal with this painful kind of registration, realignment of the data, and these images here of the red brain were our first proof of principle that, let's say, first of all, applying PLI to a series of consecutive sections may lead back to a coherent view across these sections. And this is shown here, right? So we have measured at that time 5 years ago at 60 micron resolution, and we generated something like 300 sections, rebuilt them with nonlinear registration algorithms provided by ITK. And so you can see here already the nice generation of the corpus callosum, and although you can also see some of the misalignments which are always there. But this was a first sign that it works. We can do it in 3D in principle. So we went to the next size of species, which is a vervet monkey brain. And here you can see a movie of 50 consecutive sections, non-linearly aligned, and you only see the amplitude of our birefringent signal. That means the retardation images, and we rendered the data set on our supercomputer, and you can see here in the basal ganglia already, without any kind of reconstruction, in terms of orientation or tractography, you can immediately see the large white matter components and fiber tracts, and that's pretty cool. But it took a long time. So this data set itself, just these 50 sections, are about half a terabyte of size, and yeah, you cannot do the rendering easily on your home computer. We also thought that when we want now slowly go to how to combine it with MRI data sets, it became clear very early that we should try to work a bit more with the orientations, with the local orientations, to be much closer to the data structures we can derive from diffusion MRI. So we came upon the analysis of specific kind of statistics which we can use to build from the individual orientations, orientation tensors, for example, or we can also derive some kind of orientation distribution functions, just to be able to rescale our data to the need of diffusion MRI without losing all information at the same time. So this kind of orientation statistics is always available for all of our data sets, and it also allowed us to do very first kinds of tractographic applications. And this is shown here. So in principle, this is a human brain, a part of a human brain reconstruction from the early days at 60 microns. You can see you can nicely do the tractography using DSI Studio. We did our own experiences and tractograms. And at highest level, you can even see sometimes the interweaving of vessel structures and the reconstructed fibers. But we are just at the beginning. We are no experts in tractography yet. But for setting this up, we have built a new joint French-German virtual lab, which is going for extreme scale applications for supercomputing and for exascale supercomputers. And we are convinced that once we address the entire human brain, we will need exascale computing if we want to do something like a global spin glass spectrography approach, which means that we try to optimize our tractograms at the same time everywhere in the brain. And that means that we have to deal with something like 10 to the 15th voxels, right? So this is something which just started, and I'm really looking forward to see how we can push the tractography towards PLI resolutions at large scale. So that gives already one, let's say, view on what we have done in the last 15 years, setting up this kind of PLI the PLI method, which is not anymore just a measurement. It is rather also the analysis of individual sections, the 3D reconstruction, plus the modeling behind, plus theory and simulation, always supported by supercomputing facilities. So it has already grown to a kind of quite big type of imaging. But is this the whole story? No, it is not, of course, right? There are many questions we still have to raise, and we still have to answer. And just showing you this piece of image from a vervet monkey brain, And you can see some specifics here. And one is, for example, by eye, you can really see the individual crossings here. But this is due to the fact that PLI gives us very nice contrast between different fiber structures. But if you want to go for a quantitative measurement of the orientations, you start to see that depending on the fiber structures which cross within a voxel, our simple interpretation, our simple model I've shown you at the beginning with this intensity formula, is not able to give a clever answer to the real orientation. Or you can see here some of these black things here. Some of them are due to the fact that, again, depending on the crossing angle, that the sinusoidal curves are nearly completely canceled out. So you just hardly see an amplitude. So the interpretation again becomes difficult. Or if you have a region of fibers or fiber tracts which are coming directly perpendicular out of the sectioning plan, you also see hardly any kind of signal. So how can we distinguish those situations? In addition, I mean, we are really sensitive to myelin. So can we quantify it with our data sets? When you do a PLI measurement, as I've presented up to now, which is a flat measurement, there are some orientation ambiguities inside the data set, which you do not see when interpreting individual sections, but which you can see if you start to stack them, to reconstruct them and try to follow them by means of tractography. So how can we solve them? And of course, things the people always want to have is the next step of resolution, or can we look into a voxel itself? And all these things, I think we at least we have started to tackle them over the last few months. And one is, as I already mentioned, we have started to develop together with a small company, Taurad, a new generation of polarizing microscopes, and we currently have 2 of them in the lab. And we are trying to find all the problems and try to bring them into routine operation. And the basic idea is that we are able to tilt the beam a little bit when we do the measurement. And you can see on the right this animated GIF here. So that's a measurement of tiny beads, 2 micron thick beads at different depth positioned, and then measured with a microscope, right? And you see that we are able to view the same situation from slightly different angles. And we think that this will help us to get rid of the ambiguous orientation estimation on the one hand side. We will be able to deliver level of confidence for all of our estimated orientations. And we can also get hands on, maybe you remember this prefactor in our model, where we had the dependency on the birefringent strength. And this birefringent strength is possible to extract and better distinguish from the out of plane orientation information by means of more than just one flat measurement. And this birefringent strength is clearly related to the myelin densities, what we could show by means of simulation. So we hope that bringing these devices now really into full operation, that we can solve a couple of questions and come up with even more reliable data sets at highest resolution. In addition, of course, I also mentioned this recently. We thought a couple of years ago that it is important to have simulations on the physics behind the measurement. And our very first trial was a simulation of in the optic chiasm of a seal. And you can see it here, and that was at that time the measurement. You can see the two different main orientations of the fiber tracks, including these dark bands here. These are these kind of annihilation effects when you have 90 degrees crossings at the same fraction. And that was the first time that we could, let's say, on a qualitative way, we could really rebuild it by means of a model and by means of a simulated PLI measurement. And this was the starting point for nowadays kind of approaches we have developed also together with our colleagues from CEA, from Neurospin in Paris, who wanted to do tissue modeling for diffusion MRI analysis. And so we combined our ideas and our needs so that we can now provide some tools. One tool is called Medusa, which is a very highly detailed kind of modeler tool, but we also provide a very simple one for different kind of tube-like fiber bundle models, which is sometimes much more easier to handle with PLI measurements. But you can use the same structures for doing your simulation, either in diffusion MRI or in polarized light imaging. So this is a very nice fundamental tool to bring together something like the measurement answer to the same kind of fiber structures or tissue structures. So that's a lot of fun, and we have supported. So we got support from the Human Brain Project in this kind of research. Of course, whenever you start to do nowadays any kind of analysis, you have to look into AI applications, and it definitely makes sense, for example, to combine the simulated results for PLI with the real measurements, so that you can really try to infer or predict specific signal measurements, real signal measurements in PLI by means of simulation. And this is work we have recently started together with my colleague Timo Dickscheid, who is in the same institute, and he is an expert in this kind of AI applications. And on the right-hand side, you see another starting PhD project, which is more related to the interpretation of the delineation of the structures we see. So how can we parcellate the brain based on PLI data? No one has ever done this at this level, and we have started to do this by means of self-supervised learning. To see whether we can have some clever segmentation on this, but this is really recent work, and it is not completely done yet. So we learned other things from simulation and from the tissue modeling, and from these other things, we came up with new ideas for new devices, for new types of measurements. And this is a specific kind of imaging tool we have developed, especially Miriam Menzel, who was my postdoc in the group. She did during her doctoral thesis some scattering simulations on the model tissues we have generated, and she came up with such images you see here. These are light scattering images simulated of 2 crossing fiber bundles. And here is a scattering pattern of a slightly inclined a fiber bundle, right? And you can immediately see, wow, if we would be able to measure the scattering patterns, which is typically done with X-ray, right? But we did these simulations with visible light, and we were surprised that our simulations predicted that it could be seen already at a very simple level. And from that point on, we started to develop this kind of device or method, which is called scattered light imaging, scatterometry. And what do we do here? So we have a sample and we have a monitor with accessible individual pixels, and we can switch on regions of pixels to illuminate the sample, not directly, but from the side under different angles. And then we simply measure, always at the same position, under normal incidence, how much intensity is collected. And you can do this one after the other, switching on and off the different regions of interest. And then you can have a look into the scattering patterns, the measured ones. And you can find here similar patterns for exactly those predicted situations. And those scattering patterns, you can visualize them easier when you do a profile on this, just around this situation. You see 4 different peaks. Those 4 different peaks, they do have a 180-degree difference each. And from the position of these peaks, you can derive the number of fibers and also the relative crossing of the fibers within the measured pixel, right? So you can do these, or you can acquire those kind of patterns for every pixel, currently down to something like 3 micron. And within these 3 micron, you can have a good estimate on the number of different crossings and the crossing angles. This has been described widely now, and we are currently also setting up now a system which combines 3D PLI technology and this kind of scattering in one device, so that we can really do the same measurement. And yeah, what you can really see, and we proved it by means of overlaying 3 main directions of fibers, that you can really resolve at least 3 different kind of crossing situations, right? And this is, in this context, a very important additional information we can generate. And I'm convinced that combine this with the high resolution of PLI, we can be much more accurate, especially in these difficult regions of dense fiber crossings in the deep white matter. Of course, PLI and SLI are interesting components in the let's say towards connectome data, but of course we are all interested in much more in the different scales we can acquire, and it's clear that diffusion MRI works at different levels. It is getting better and better depending on the devices we can use. And also, since it is applicable to postmortem brains, where you can extend your measurement time for a couple of days, it's possible. You all know that possibly better than I do, really down to few hundreds of microns. Then we have this PLI application, or comparable at this level, the OCT. So something in between the highest resolution, in between individual fiber imaging and this diffusion MRI. And I'm talking for the about to photon fluorescence microscopy, for example, which might give us the next level of information. And this is something we have started to study through the Human Brain Project, combining different groups from Neurospin doing the diffusion MRI, Jülich doing the PLI and SLI, and Lenz in Florence doing the 2-photon microscope. And this is what I'm going to present you now. And for me, it's really important that you understand that multiple modalities at this level of resolution is only interesting if you are looking into the same tissue. And no, it's not only interesting, but it is really important that if you really want to understand the different scales of the connectivity, you need to look into the same tissue. And this is our first proof of principle in the context of the Human Brain Project. We sent some postmortem sample, temporal lobe, to Neurospin, and they did a delineation of the let's say measurement with the 11.7 Tesla preclinical scanner at that time at Neurospin, and they did the analysis of the inner connectivity of the hippocampus. So this has been reported already in 2018. Then we received the tissue back, did the sectioning, did something like 600 section measurements with PLI, and it took us a while to 3D reconstruct. Here you can see, let's say, the cytoarchitectonic map, the big brain from Jülich, and embedded the 3D reconstruction of the hippocampus. And you see there are still some misalignments, but in principle, the reconstruction is at a very high level here. So we were successful to align about 600 consecutive hippocampus data on PLI. And if you have a closer look to an individual of these sections, you can also see this is a very, very new kind of technique we use. You can see the fibers, cortical fiber tracts, or tiny bundles, however you would like to call them. But you can also see these bright dots, which are indications of cell bodies. The transmittance value we can extract, so the mean value of the PLI measurement can give you the idea of individual cell bodies, and combined the FOM and the transmittance image infused in a clever way, you can see both. So you can now try to study the distribution of cell bodies, including the fibers. But I have to say, the cell bodies, they are not of that nice shape, as you know from a specific staining. But it is taken in the same measurement, so it comes for free for us. And for the next kind of studies, we will also apply post-staining with Cresol Violet, which also works on the PLI sections, so that we can have a clear assignment of these cell distributions to the well-known cytoarchitecture. So that's quite nice. That's currently unpublished data, but we are heavily working on this, and the data will be publicly available through the HPP Atlas, through the so-called eBrains platform. Next step is to photon microscopy. By luck, we observed that when we wash our PLI preparations, our PLI sections with PBS for 3 months, then the tissue becomes autofluorescent, but in a way that only the myelin becomes more autofluorescent than the environment, which means that once we have done the PLI section imaging, we can apply this kind of washing, which is, in the end, we named this MAGIC protocol. And this MAGIC protocol is based on the fixation of the tissue with PFA, right? We embed the tissue in glycerol, and afterwards, after the PLI measurement, we try to remove the glycerol by means of PBS washing. And this gives rise to this kind of contrast imaging by means of TPFM. And in the end, you can see two compartments. You can see the fibers, which are shown here in green, in the green channel. But for the human brain, usually we are dealing with aged brain. You can also see a lot of lipofuscin pigment, which also becomes very prominent. So in the end, we can measure within a PLI section directly the 3D content and the orientations of the fibers. And this is what we use to compare the results, the orientations. And we did this, one of the measurements in a mouse brain section, and you can see here 4 different masks inside the PLI fiber orientation map, and these masks have been aligned. They have been measured with TPFM and aligned properly, and then we compared these bundles you can see here in the pallidum, and they agreed quite nicely. So and here, this is the very last kind of imaging I would like to present you, which also works on PLI data. And this is on the left-hand side. You know this. It's a PLI fiber orientation map from a sagittally sectioned vervet monkey. And we are here in the LGN region. And on the right-hand side, you see the same section post-stained by means of immunohistochemistry, and you can see 3 different colors. Each color has stained one of those calcium binding proteins. And this is the reason why you can see later, when we do the movement across the section, or already here, you can see these different colors, which indicate which region in the brain is mostly covered by these or those or whatever kind of calcium binding proteins. And this is quite nice, and we will apply this also in the next studies wherever we can do this. This kind of very specific staining has been done in Amsterdam by means of Roxana Koymans. So all these guys, they give us additional information on the different levels of connectivity. And I hope in not so far future, we will be able to combine this information, because they come from the same type of tissue. Even if you treat the tissue between the imaging sessions seriously, it should be much more easy to combine them and to compare them as comparing different brains at this high resolution. And so before I come to the summary, the final summary, there are even much more imaging applications we have tried and which work on PLI tissue. So that's the reason I see PLI from our point of view as a kind of bridging technology, and we try to prepare the brain sections in a way that we can apply all of these guys here one after the other if we want to. So to those belong also the MALDI imaging, matrix assisted laser desorption ionization, mass spectrometry imaging. It's a difficult name. With this kind of MALDI imaging, we can specify the type of lipids which are present locally. Scattering, I presented the visible light scattering, but of course you can use neutrons. We did. We are currently preparing or finalizing a paper on that, and X-ray scattering has already been published. It is possible also to do it on the PLI data, and very recently, together with SAIS, we had a tiny kind of project, but we managed to prepare our sections for electron microscopy in addition, so that we can even learn about also the, let's say, the distribution of myelin to be able to transfer this to the interpretation of all the other technologies and vice versa. So I hope that this was an interesting approach for you. I would like to close this session with a new kind of animated video we have produced. It takes 3 minutes. And sorry for my overtime, but I think it would be really cool to show this finally and enjoy it. I have to switch off my earphones, so don't worry, because you should hear the sound. Can you hear me now? Okay.
Okay, thank you very much. That's the end of my talk, and I'm open to any question.
Amazing. Thank you so much, Markus. I really, first of all, I should say that I really see potential for you for a whole animated series where you star as a superpower superhero of optical imaging. And thank you so much for a great presentation of all this, great overview of all this amazing work that you guys are doing. I specifically admired your setup in one of the very first slides where you where the brains are sectioned and mounted semi-automatically, I guess. So I'm assuming that something like that is not something that you can just get off the shelf. It's a very customized type of hardware. So can you talk a little bit about that, and what is the, more generally, what is the major challenge for you for scaling to the whole brain? Is it the hardware? Is it the misalignment? Is it the data size?
It is all of that. That's the main problem. So it's really like the hardware you can scale a little bit up, right? So all these devices I've shown are not completely automated yet. So we are just building a robot system that is able to upload every 5 hours a new section. That's one part, and from these devices you need more than one, right? So that's a similar way as Katrin Ammons is setting up for the Cyto architecture. So buying a farm of devices, that's one thing. Then you have to deal with the data. I think it's not that a problem, because in Jülich we really have the infrastructure for this and the willingness to do this, to realize all these uploading stuff, and that's not the biggest issue. And then of course the 3D reconstruction is the most important issue. So you destroy the tissue, that's for sure. You destroy the wiring at micro scales, and I'm sure you will not be able to rebuild this at micron, 1 micron precision everywhere. However, so when I started 15 years ago, Carl Zille said, we know everything about registration, we can do it. It's no problem at all. So over the years, I lost a little bit the trust in that. But quite recently, we found a way, especially the group of Timo Dickscheid, they found a clever way, also supported by AI approaches, to find sectioned cell bodies in neighboring sections. And those guys are the best tiny landmarks you can find. So if you can really do, let's say, already a nice kind of pre-alignment, as we do now for the PLI stuff, then you already have a quite good situation to be able to find sectioned cell bodies. So that really means you cut through one cell body and you see it in the bottom of the one section and on the top of the other.
That's amazing.
And there are many of them. So we proved this with Cyto architectural stainings. And that's one reason why we try to do also the post staining on many of these sections, to have this possibility available. Because then you can be much more precise locally, that you destroy sometimes regions of interest completely and they are forever gone. That's life, right? But I think we are getting much closer to nicely realigned sections now.
That's amazing. We'll be watching out for what comes out of your group next. Thank you again.
You're welcome. Thank you.
Thank you, Markus. The video was fantastic. and everything else too, obviously. We have a question from Chao. So Chao, if you want to unmute yourself.
Okay. Very nice talk. I work on the OCT's work. I work on OCT at the center. Can you comment more on the tilting illumination? Can you get illumination angle from just inclination angle from just one illumination? Is that for the unreliable voxels from the high inclined fibers?
So yes, we have one illumination source. That's right, and we use the I'm missing the English name. So we can select the specific incoming beam orientations by plus minus 5 degrees on that, right? And we think it is enough to judge whether a fiber, if you do a measurement with polarization microscopy just in a flat way of illumination, you cannot distinguish these two situations by the measurement. But once you tilt a little bit already, you see an effect on the sinusoidal curve, and that's enough to get an idea on which of these possibilities are more likely to be present. And that's the basic idea on that. And we think from point of simulation that these 5 degrees changes of illumination angles might do it.
The 5-degree tilting, you mean, right?
No, it's always, well, it's always relative to the sectioning plan. Right, 5 degrees means you have the tissue, and then you can, let's say, decide whether the light beam goes in this direction or has a slight angle to the perpendicular inclination. And this is what we can select by means of these new devices.
Okay, thank you.
So it's all about, since we measure in transmission, it's all about the relative angle between the incoming beam direction and the orientation of the local fibers. And you can do two things with the large area polarimeter. The coarse one, we tilt the tissue itself. So it's really a mechanical tilting, but we don't change the illumination. But for the microscope, of course, we cannot simply tilt something, but we can tilt the light pathway a little bit. And that's the same. It's just a relative angle between both of.
Yeah. How much do you have to tilt the sample?
So plus minus 5 degrees.
Oh, I see. Sorry. Yeah, I missed that. Okay. Thank you.
Yeah. You're welcome.
All right, I don't see more questions, but I'm gonna ask one. So I'm not sure how computationally expensive the simulations are, but I was curious if you tried more complex sort of like configurations. And also whether I don't know if the prediction of the model do they depend on anything that is specific of the tissue? Like, yes. I don't know, myelin thickness and, yeah.
Yes, so that's a very good question. So we started with the simplest tubes. Then we will write the thickness of the tubes, and we will write let's say the physical compartments, which means for PLI it's important to specify the local thickness of the myelin, for example. Doing MRI. So the diffusion experiments with these, the membranes get some specific physical parameters. So it's not only something like a formal tube, but we can relate every compartment to a specific kind of physical property. And this is what we need. For many of our interpretations, the simplest fiber bundles do fine. But it's clear the better we also know these or apply these other technologies with highest resolution, they can give us new models, right? So we will also use these measurements to generate new models to be much closer to realistic phantoms. But we are not quite there yet. But I'm hopeful that once we can do this electron microscopy on a larger scale, that might really help to improve the individual compartments significantly.
Okay, thank you. Well, we'll wait for that then. Oh, we have one more question. I think this is gonna be the last one. So, okay, so Maria, you can ask the question if you want.
Hi, so thanks for a really nice presentation. I'm particularly impressed with the granular resolution, and I was wondering that how much does if the ultimate goal is to develop a 3D atlas of these fibers, then the individual variability towards that goal, is that a big issue in what you've encountered so far?
That's a big issue, and it is important. You know, from Jülich, the Jülich brain atlases, they are based on something like 10 to 20 different brains, considering the variability. I'm pretty sure we also have to go this way at some point, but currently with the equipment I have now in hands, it might take something like 2 years to measure the entire human brain, one of them. This means it will, not having a measurement farm in hands, it will still take many years to get there, to at least have some kind of variability. But what we are currently discussing is to focus on specific regions and at least try to find out these local variabilities. That might be a reasonable near future step.
Okay, great. Thank you. I was just also wondering about across the age span. Right now, the focus is on adults, right?
Yes. Yes. So since we depend on these donors, most donors are older than 70 years on average. So we always have this atrophic or whatever effects inherently present.
Right.
Yeah.
Okay. Thank you very much. It's really wonderful.
Thank you very much.
All right. Well, thank you again, Markus, for this incredible work and great talk. And thank you everyone for attending today, and have a magnificent rest of your day.
Thank
Bye.
you very much.